Hi, everyone. Welcome to the video where I will go through some of the practice questions that I gave you last week. Okay, so let's start with question 1. Let's read out loud. So question 1 says, let H1, H2, and H3 be statements that a certain coin lands heads the first, second, and third time it's tossed. Right, so you toss a coin 3 times, and H1 means it landed heads on the first time, H2 means it landed heads on the second time, and H3 means it landed heads on the third toss. So suppose that this coin is tossed 3 times and that getting tails is equivalent to not getting heads. Right? If it's not heads, then it's tails. Express each of the following as simply as you can in the language of propositional logic using only H1, H2, and H3. Okay, so the first question asks, okay, how can we express the statement the first and second tosses both land heads? So we know that H1 means that it landed heads on the first toss, and we know that H2 means that it landed heads on the second toss. Actually, H3, it doesn't matter what it is. We can forget about it for this statement. The question is, which connective are we going to put over here? But note that it says the first and the second task both land heads. So if we put an or over here, we just need one of the outcomes to be heads, right? It could either land heads on the first or land heads on the second, but we want both. So actually, this should be the and that's it. Now, the more interesting one is, how can we express that there are at most 2 heads? At most 2 heads, what does that mean? So let's write it in words. We can have either the case, right, we have 1 heads, or we can have the case where we have 2 heads. Now, how can we express that we only have 1 heads? Well, let's look at all the possibilities. We have 1 heads when we have H1, not H2, and not H3. And how do we connect them? Well, we connect them with the and over here. That's one possibility, but it's not the only possibility where we only have 1 heads. The other possibility is where we have not H1, we have H2, and not H3. So here, that's when the second toss lands heads, but the other 2 landed tails. And similarly, we can have not H1 and not H2 and H3. So these just mean the coin landed heads on the first toss, coin landed head on the second toss, and the coin landed head on the third toss. Okay, but we're not done with the statement of there are at most 2 heads. We just consider the case where there's 1 heads, which now we could have 2 heads, right? We could have either on the first and the second toss, so that would be H1 and H2. And we're not done here because we want exactly 2 heads, right? So we're going to put not H3. So the coin lands heads, heads, and tails. That's 2 heads. Then we have what? Heads, tails, heads. Right? So we could have H1 and not H2 and H3. And similarly, we might have not H1 and H2 and H3. Now, are we done, actually? So you might note that here, there's one possibility that we didn't consider yet, which is at most 2 heads, it includes 0 heads. So we have another case, which is 0 heads, and that's when it's all tails, right? So we have not H1, not H2, and not H3. So it's a bit long to write, but this writing it logically really sets every possible outcome apart. And so right now we're done. We can erase the words, and right, you can just connect all of these with an or. So or this, or this one, or this one. Right, and we can add an or over here, right? You can write them all in a single line, but maybe it's not so necessary to do that. But these are all the possible outcomes, and you connect these with or, right? It's either it lands having Emma's two hands, either you have one head that's in this particular way, or in this way, or in this way, or you have, say, no heads, or you have two heads in this way, or this way. Okay, I hope this helped. Let's look at another of the questions. So to identify the cognitive bias, I think this should have been a rather straightforward exercise, but the question was, that fellow is wearing a cowboy hat and a Lone Star t-shirt, right? It's more likely that he's a Texan and an accountant rather than he's an accountant. But right, so just remind ourselves why this is maybe this is a cognitive bias that we have. Well, because, well, if we see a fellow that has a cowboy hat and a Lone Star t-shirt, we might really have a big possibility space over here that we think that they're a Texan. And think that it's very unlikely for them to be, say, an accountant. However, what we're doing here is that the person is thinking that it's more likely that they're a Texan and an accountant. So they think this shaded part over here, that is more probable than he's just an accountant. So you should see that we're violating on probability rules, and this is just the conjunction fallacy. This is very similar to the Linda example that we saw in class. Okay, so now let's look at this question. So for each of the following, say whether it's true or false, and maybe explain why. So the propositions are independent, then they must be mutually exclusive. Okay, so let's assume that A and B are independent. Now, are they mutually exclusive? Well, no, they cannot be mutually exclusive. Because if we suppose that they're mutually exclusive, then that means that they never occur at the same time, right? They can never both be true at the same time. So if I tell you that A is the case, then this gives you a lot of information about B. It tells you that B is not the case. But remember that independence is supposed to, A and B are independent if A and B give no information about each other. So this is false. So we went one way. Now let's see, if propositions are mutually exclusive, then they must be independent. Is that true or false? Actually, this one is also false. But here there is a case where they can both be, where a proposition can be mutually exclusive and independent. It's just not always true. In fact, it's only true in a very special case. Suppose that A and B are mutually exclusive. Now you might ask, do they have to be independent? Well, they're only, remember that A and B are independent only if A and B is equal to probability of A times the probability of B. right? That's by rule 5. You can put rule 5 over here. This isn't rule S, it's rule 5. I see that I missed time. Now, remember that A and B, if they are mutually exclusive, right, this is equal to 0 because their intersection is 0. So that would mean that either this is only the case when the probability of A is 0 or when the probability of B is 0. But if the probability of A and the probability of B are both greater than 0, then they're not independent, right? Because we know that they're mutually exclusive. If they're mutually exclusive, probability of A and B is equal to 0. And we know that if they were independent, the probability of A times the probability of B would be equal to probability of A and B. But this is only the case when either probability of A or probability of B is equal to 0. And so if they're not equal to 0, then they can't be independent. So it's false in general. Okay, so how about the last question? So if the probability of A is equal to the probability of B, then A and B must be logically equivalent. And this is, again, also false. What's true is that that the other way around. If A and B are logically equivalent, then probability of A is equal to probability of B. That's by rule 3 that I gave you. But it's not the case that if probability of A is equal to probability of B, then they must be logically equivalent. So here's just one counterexample, right? You might have A and B, and they both take 50% of the space. And so they have the same probability, but they're not logically equivalent, right? They're not saying the same thing. In fact, they're mutually exclusive in this case. Okay, so let's look at our last question. So show, using the definition of conditional probability, that if A and B are independent, then the probability of A given B is equal to probability of A. So let's go this slowly step by step. So what do we know? We know that A and B are independent. We're going to assume that, right? Because it's a conditional statement. If A and B are independent, then blah. So let's assume A and B are independent. What do we know about independent statements? The only thing we know is by rule 5. So by rule 5, probability of, I'll let you a second to think. Well, probability of A and B is equal to the probability of A times the probability of B. Okay, so I want to show that probability of A given B is equal to probability of A. Let's write probability of A given B. We want to get probability of A here. Can we get here? We don't know. Let's see. So just by definition, remember this is a definition of conditional probability. This is equal to probability of A and B over the probability of B. Right? This is by definition of conditional probability. But now note that we know what probability of A and B is. Namely, it's probability of A times the probability of B over the probability of B. And we can make this jump over here from, you can call this star, from star. Right? It's by the fact that they're independent, the probability of A and B is equal to probability of A times the probability of B. So we have this over here, and now we can cancel out the probability of B, and that's just the probability of A. So this makes sense, right? The probability of A given B, if A and B are independent, if I tell you that B occurs, it gives you no information about A. So probability of A given B is just the same as a probability of A. Okay, so that's all the questions I'm going to go through. I hope this helps. And yeah, thanks for watching.